Hello friends, welcome to the session. In this session, we discuss Bohr's atom model or Bohr's model of hydrogen atom. Okay, and specifically, we discuss the conceptual part of the postulates of Bohr's atom model and the numericals related part we discuss in the next session. Okay, let us start. Let me share the screen over here. Yeah. Yes. See, Bohr's model of hydrogen atom. Bohr's model of hydrogen atom. Hydrogen atom. Or we also call it as Bohr's atom model. Right? Actually, in the year 1913, in 1913, Bohr has proposed few modifications to Rutherford's atom model. In the year 1913, Bohr has proposed a few modifications to Rutherford's atom model. Rutherford's atom model by applying Planck's quantum theory. By applying Planck's quantum theory. Planck's quantum theory. Okay, and he has succeeded in explaining few very important characteristics of the atomic structure. Let us see what are those in the postulates. Before that, what is the point he has applied? What is the point he has leveraged in explaining this postulates from Planck's quantum theory? Let us see. According to Planck's quantum theory, the energy will be radiated or absorbed. Irradiated means emitted, or radiated or absorbed in the form of discrete particles or packets of energy. The energy can be emitted or absorbed in the form of packets, and these packets are called as quanta, and later they have named as photons. So according to Planck's quantum theory, according to Planck's quantum theory, energy will be radiated or absorbed in terms of packets, called quanta or photons. And here the energy of a single photon, according to Planck's quantum theory, the energy carried by a single photon is given by the energy of a single photon. Energy of a photon or a single photon is given by E equal to h nu or hc by lambda, where h is Planck's constant, nu is frequency of radiation, c is speed of light in free space, and lambda is wavelength of radiation. So where h is equal to Planck's constant, and it is a universal constant. Keep in mind, Planck's constant, its value is 6.623 into 10 to the power minus 34 joule second. Minus 34. Okay, write this clearly. Minus 34 joule second. Some books may give you 6.6 only to one decimal point. Okay, 6.623 into 10 power minus 34 joule seconds. And h is Planck's constant, and nu is h is Planck's constant, and the nu is frequency of radiation. radiation. And here c is speed of light and lambda is wavelength. Lambda, nu is frequency, lambda is wavelength of radiation, emitted radiation or absorbed radiation. And c is equal to speed of light in free space. Its value is given as 3 into 10 to the power 8 meters per second. It is a constant. You have to remember this value and Planck's constant value also. Okay. By making use of this point of Planck's quantum theory, Bohr has proposed the postulates of atomic model called Bohr's atom model or Bohr's model of hydrogen atom. Let us see what are those postulates briefly. Okay. So let us write down next subheading, postulates of Bohr's atom model. Write down next subheading. Yes, postulates of Bohr's atom model or Bohr's model of hydrogen atom. Bohr's model of hydrogen atom. Postulates of Bohr's model of hydrogen atom. So in the first postulate, he has proposed that, Bohr has proposed that the electrons hereafter we represent like this, electrons. Okay, the electrons revolve, and actually in to discuss this you have to just observe a few points in Rutherford's model and how he has modified those by applying Planck's quantum theory. In already Rutherford has concluded with the help of alpha scattering experiment that the entire positive charge of the atom resides at the center called central core called nucleus, right? That is what he already has concluded by using the experimental results. This point he also has brought, and he has, in addition to that, he has modified some suggestions by applying this Planck's quantum theory. So what he has modified is, and what he has proposed in the postulates is, the electrons revolve around this nucleus, positively charged nucleus, in certain discrete allowed circular orbits, certain discrete allowed circular orbits. And the force, whenever a particle of mass m is moving in circular path, means it should be having a force will be holding that particle in circular motion, that is called a centripetal force. And the required centripetal force here is provided by electrostatic force of attraction between positively charged nucleus and the electron, negatively charged electron. So that is that is what he has proposed in the first postulate. So let us write down that the electrons revolve in certain allowed circular orbits around the nucleus, and the required centripetal force is provided by centripetal force for whom? For the electrons. The required centripetal force for electrons, you can also write that the required centripetal force for electrons is provided by by whom? By the electrostatic force, or Coulomb force we call it, is provided by the electrostatic force of attraction, or simply you can say by the electrostatic force between the electron and the nucleus, and according to this you can say that centripetal force is represented as mv square by r. It is provided by electrostatic force. So electrostatic force expression I will write here. It will be expressed as a k into q1 q2 by r square, where k is 1 by 4 pi epsilon naught. It is a constant. Here in this case, when an electron is revolving around the nucleus, negatively charged electron around the positively charged nucleus of charge Ze, q1 is E, q2 is Ze. Then by substituting this, we will write 1 by 4 pi epsilon naught into Ze square by r square. We will take this as equation 1 from the first postulate. Is it clear, everyone? In the first postulate, Bohr has proposed that electrons revolve in certain allowed circular orbits. That the concept of circular orbits is proposed by Bohr only. Okay, circular orbits around the nucleus. The required specifically that what you call allowed or discrete circular orbits. Concept of discrete circular orbits is proposed by Bohr. Okay. And the required centripetal force for the electrons to be in circular path is provided by electrostatic force or Coulomb force of attraction between the electrons and the nucleus. That is mu square by r equal to 1 by 4 epsilon into Zg square by r square. We will take this as equation 1. We make use of these equations later on to derive different expressions like radius of an electron in nth orbit, velocity of electron in nth orbit, and etc. So you have to remember these points. First postulate means you have to keep this equation in mind. Okay. Yes. Let us see the next second postulate. What Bohr has proposed in second postulate. In the second postulate, he has proposed that second postulate, just a second. Yeah. In the second postulate, Bohr has proposed that these electrons revolve only in allowed circular orbits for which the angular momentum is integral multiple of h by 2 pi. So that can be expressed as like this. Write down this, everyone. The electrons revolve only in allowed circular orbits for which the angular momentum is an integral multiple of h by 2 pi. So how can I express that is angular momentum is expressed with letter L. L is equal to in the 11th standard we have already studied about angular variables in different chapters, system of particles, etc. So here angular momentum is given by mvr. L is equal to mvr. It is equal to integral multiple of h by 2 pi, means an integer n into h by 2 pi, where n is an integer. So it is also called as a principal quantum number. We'll take this as equation number 2, where n is equal to principal quantum number. And it takes the values, of course, 1, 2, 3, and so on. Okay, integral values. Okay. And this condition proposed by Bohr in the second postulate is also called as Bohr's quantization rule. What is this is called as? This condition is called as Bohr's quantization rule. Bohr's quantization rule. So what is Bohr's quantization rule? Based on these conceptual points also, you may get some objective questions in NEET point of view, JEE point of view. So which of the following expressions represent Bohr's quantization rule? MVR is equal to 2 pi by h, or 4 pi by h square, or h by 4 pi, h by nh by 2 pi, like this. So you have to keep in mind that what is this Bohr's quantization rule? It says is angular momentum of an electron in a given orbit or in a discrete orbit is equal to integral multiple of h by 2 pi. And these orbits, allowed orbits, are also called as the stationary orbits. What orbits? Stationary orbits. So that also you have to write down, and you need to have an idea about what are the stationary orbits. Okay. So what are the stationary orbits? Just I'm giving you an idea. You can note it down. You can copy it down. Stationary orbits are nothing but the orbits in which the electrons will have an angular momentum equal to integral multiple of h by 2 pi. Then such orbits are called as stationary orbits. Is it clear? The electrons revolve only in allowed circular orbits. These allowed circular orbits are also called as stationary orbits. So what are stationary orbits? The orbits in which electrons will possess angular momentum which is equal to integral multiple of h by 2 pi. Such orbits are called as stationary orbits. Stationary orbits can also be defined as the orbits in which, as long as, or you can write down here specifically this definition. Just a second. Yeah. Write down like a subheading stationary orbits, and write down the definition of stationary orbits over here. Stationary orbits. Stationary orbits. So what are stationary orbits? So the one way you can define them as the orbits in which the angular momentum of electrons, the angular momentum of electrons is equal to h by 2 pi are called h by 2 pi are called, these orbits are called stationary orbits. Stationary orbits. Is it clear, everyone? Stationary orbits. This can also be defined as the orbits. This is one of the very important way of defining stationary orbits. By making use of this, Bohr has proposed the next postulate called third postulate. The orbits in which as long as electrons revolve, they neither radiate energy or absorb energy. That means the electrons will radiate or absorb energy only when they move out of a given orbit. Maybe that means they jumps from a given orbit to higher or lower orbit, then only energy emission or radiation or absorption will take place. Or if otherwise, if an electron is revolving in a particular orbit or particular certain allowed orbit called a stationary orbit, the electron will never radiate energy or absorb energy. Is it clear? So the orbits in which, as long as electron revolve, okay, then the orbits in which, as long as electron revolve, they neither radiate nor absorb energy. Such orbits are called energy. Such orbits are called stationary orbits. Stationary orbits. Is it clear? Right. By making use of this point, Bohr has proposed the next postulate called third postulate. Let us see what is that third postulate. These are different ways of defining stationary orbits. Don't confuse with these points 1, 2, and third, next point 3, which you are going to give, is nothing but third postulate, not the third definition of stationary orbits. Okay. So third postulate. So what is the third postulate of Bohr's atom model or Bohr's model of hydrogen atom? In the third postulate, Bohr has proposed that the electrons will jump, whenever an electron jumps from one state to another state, then the electron will radiate or absorb energy in terms of photons, right? Whose energy is equal to the energy difference between the energy levels from higher to lower or lower to higher, from which orbit to which orbit it is jumping. So let us write down this. Let's write down this. So in the third postulate, what it says, when an electron jumps, third postulate, when an electron jumps from, when an electron jumps from one stationary orbit to another stationary orbit. When an electron jumps from one stationary orbit to another, a photon is emitted or absorbed. A photon is emitted or absorbed. A photon is emitted or absorbed with energy equal to the energy difference between the energy levels. I'm repeating here. Let us see here once again this. When an electron jumps from one stationary orbit to another stationary orbit, a photon is emitted or absorbed with energy equal to the energy difference between the energy levels. More specifically speaking, when an electron jumps from a higher energy level or higher stationary orbit is also called as energy level. Keep this in mind. If you want, just you can write a note. Orbit can also be called as energy level. Orbit can also be called as energy level. So when an electron jumps from one stationary orbit to another stationary orbit, or one energy level to another energy level, a photon is emitted or absorbed. With energy equal to the energy difference between the energy levels. Is it clear? So more specifically, I will give you here. So here, let us say, for example, when an electron, say if this is first orbit, let us say just we have a nucleus with a positive charge. There are different orbits are there, different orbits. Just you have to consider proper circular structures over here. Okay, yeah. So what kind of the circular structures these are all? Let us remove them. Let us draw properly. This is one circular orbit. This is another circular orbit, and let us say an electron has jump. This is nucleus, and let us say this is the first orbit n equal to 1. This is second orbit n equal to 2. This is third orbit n equal to 3. When an electron jumps from third orbit to first orbit, let us say, when it jumps means it is falls down or jumps, whatever, any word you can use. When it jumps from third level to first level, that is usually third level will have higher energy, first level will have lesser energy. That we will see. We will try to derive the expression for those energies. Then when it is jumping from higher energy level to lower energy level, it radiates or emits a photon with an energy. The energy of photon already we have discussed that, whose energy is equal to h nu, and this energy is equal to the energy difference between these two energy levels. If it jumps from 3 to 1, what is energy difference between these two levels? That much energy photon it will radiate. Whereas if it jumps from 3 to second level, what is energy difference between these two levels? That much energy photon, or it will emit a photon whose energy equal to the energy difference between these two energy levels. That is emission of energy, how it takes place. Whereas how absorption of energy takes place. When an electron is revolving in first orbit, it continues to be in that orbit only. When if you make the radiation to incident on it, a photon to incident on it, whose energy is equal to the energy difference between these two states, then it jumps to this energy level. Or if the energy of the incident photon is equal to the energy difference between these two energy levels, then it will jump to third energy level. And likewise, the energy will be absorbed or emitted. Is this clear? Yes. Then with this, I hope the postulates of Bohr's model of hydrogen atom are Clear? In the next session, we will discuss how to derive the expressions for radius, velocity, and energy of an electron in nth orbit. So I believe the postulates of this Bohr's atom model are clear for everyone. First postulate, second postulate, third postulate. First postulate is called as first postulate gives this equation, second postulate gives this equation, we also call it as the Bohr's quantization rule, and the third postulate gives here based on this I forgot to give a mathematical expression for this. Third postulate, as it says that when an electron jumps from an energy level to another energy level, a photon is emitted with energy equal to energy difference between them, right? It is given by, you have to write down this, it is given by h nu is equal to, here this is energy of the photon is h nu. H nu is equal to energy difference between the energy levels, E final minus E initial. We'll take it this as equation number 3, and this equation is called as Bohr's transition rule. Bohr's transition rule. This is also called as Bohr's transition rule. I hope these things, these postulates are clear, everyone. Yes, I'm winding up now. We'll meet in the next session. Okay, take care, everyone. Bye bye.